This video we'll talk about the action potential, what action potential actually meant for, what does it do, and how the whole process of action potential, how it generate, how the process of transmission of impulse act on the neuronal membrane. We'll study this. So first we have our topic, the heading, the action potential. What is action potential? Actually, the action potential, these are the electrochemical fluctuation that sweeps over the over the membrane of axon, or we can say the over the membrane of our neuron, right? Through which the electricity or the electric current is transmitted in the form of electric impulse, and the signal is transmitted to our spinal cord. For example, we have this schematic presentation here. Here we have our, for example, neuron, right? So if action potential is generated here, so action potential will be it's getting sweep over in the form of electric impulse, and then the signal will transmit to our spinal cord, and from our spinal cord to the central nervous system. So this how the whole process of generally the action potential occurs. So when we are studying action potential, we should be very familiar with the many terms. There are a lot of terms. For example, in case this is our typical presentation of our one action potential, right? So in action potential first we have a threshold potential. When the when we've reached to the threshold potential, then we have a process of depolarization, then after repolarization and hyperpolarization. So we have to study in this video tutorial about these things. So let's just continue, right? Okay, so let's begin, right? So when we have one threshold potential, how we can reach to the threshold potential? Whenever there will be a stimulus, right, and it is capable enough to produce a stimulus which is strong enough to reach at the threshold level, which is at the minus 55 millivolt. This is the diagram of action potential, typical action potential. And this minus 85, what does it represent for? This is the equilibrium potential for the potassium ions, right? Minus 70 millivolt, this is the resting membrane potential. This is just the membrane potential, or we can say the charge of the membrane when it is at rest, which means that when there is no stimulus, minus 70 millivolt represent that value when the membrane is at rest, that is, there is no stimulus right there. Whenever there will be any kind of stimulus, then it just fluctuates, it just triggers it towards the minus 55 millivolt. But sometimes the threshold potential cannot be reached. For example, if we have very less strong stimulus, for example, if the stimulus is very small and it is not able to do it, so it could not reach to the threshold. So if it could not be it could not reach to the threshold, then the action potential cannot occur. For the successfully action potential, for a successive action potentials, we have to reach to the threshold. Once the threshold is reached, action potential has to occur, right? So at the value of minus 55 millivolt, the threshold it reaches to the threshold, right? It reaches to the threshold point. So when this reaches, at the same time, the command sends to the sodium gated voltage channel, which we'll see in later on in this video, and also to our K positive channels, voltage gated K positive channels. And but the K positive voltage gated channel, which we call normally the VGC, they are very slow. They are open slowly, they also close slowly, so they will close later on in the action potential. But here the Na positive VGC, they gets open, and when they will open, a lot of Na positive will come inside the cell. What actually I mean is that from the extracellular matrix, there is a large abundant amount of Na positive, so a huge amount of Na positive, as there will be diffusion. So when the threshold will be reached, the Na positive will be coming inside the cell, or we can say the influx of Na positive will occur, which results in the net positive gain inside the cell, which is in the intracellular matrix. So as we know that generally we have negative charge inside the cell membrane, or we can say in the cell membrane of a neuron. But what here happens is when there will be the huge influx of Na positive ions, the polarity will be the polarity is getting distorted, which means that positive charge is neutralizing the negative charge, which we call that depolarization. So there the D stands for the depolarization, and the process of depolarization will occur. But at the level of plus 30 millivolt, what just happened that when the level is we have for example, we have a voltage gated channel. There we have one inactivation gate for the sodium VGC. The inactivation gate, which gets closed when it reaches to the plus 30 millivolt. We will see later on in this video, but the inactivation gets closed, so there will be no later on influx of Na positive inside the membrane. But what happened in this time, that at this time when the inactivation gate gets closed, so there will be no influx of Na positive channel, but at this particular moment the sodium voltage gated channel that opens, which we'll see later on in the video. And when the K positive channels, voltage gated channel, they open, there will be huge efflux of K positive, as it all happening in the laws of concentration gradient. As the concentration of the K positive is inside the cell is more and outside the cell is less, so there will be huge amount of efflux of K positive along its concentration gradient. So as the K positive is getting outside the cell, so it re-establishes its polarity. What does it mean? When Na positive is getting inside the cell, large amount of positive charge is getting accumulated in the cell, so the net positive charge is increased via the efflux of Na positive. We have K positive inside the cell, and now we have Na positive inside the cell, so there will be more amount of more amount of positive charge inside the cell. But when the K positive VGC, they are getting open, the huge amount of K positive will getting outside the cell, which just re-establishes the negative charge, or I can say that there will be the flow of positive charge. So that's why we call it the process of repolarization. Now the process is getting established, the negative charge is getting established by the K positive VGC, and as I have told you that the K positive just open slow, so they will be closing slow. So when it will surpass the minus 70 millivolt value, and then it is just getting to the downside, and then we have the concept of hyperpolarization. The cell will be getting in the state of hyperpolarization. Here at this particular moment, what just happened that the sodium, the potassium, I'm sorry, the potassium VGC, they will be getting closed at this particular moment, and then the hyperpolarization is carried by the action of our sodium potassium ATPases, the sodium potassium pump, which brings inside the 2K positive chi ions, and getting the and get outside the 3 Na positive ions. We'll see now in this video later on that what the whole process is going on, right? So that's our action potential. We have the process of depolarization, where we have a huge influx of Na positive. Then we have the process of repolarization, where we have the efflux of K positive, and then we have a hyperpolarization when there we have the negative charge beyond the minus 70 millivolt, the value of minus 70 millivolt, which is the value for the resting membrane potential. The negative charge will surpass this value, and it is getting close to the minus 85 millivolt. What is minus 85 millivolt? This is the equilibrium potential for K positive ions. The equilibrium potential for our Na positive is plus 65 millivolt. Now here we have a very interesting concept, that if inactive gates of sodium voltage gated channel, they will not open, then this positive charge, we have the plus 35 millivolt, it is getting in the equilibrium, right? So we have equilibrium level at the plus 65 millivolt. So what just happening is that Na positive is getting inside the cell until the equilibrium potential is achieved, right? So it will be getting inside the cell till the value of plus 65 millivolt. But at the value of plus 30 millivolt, what just happened, the inactivate gates are getting closed, and the source potassium voltage gated channel, they will be open. So there will be influx, so there will be efflux of K positive ions outside the cell. So that's how the whole process occurs. So the value is quite it is reaching to the minus 85 millivolt. But then as I've said, that by the action of our sodium potassium ATPases, the polarity again get re-establishes, as there is the net loss of one positive charge in each action of our sodium potassium ATPases, right? Three positive outside, one positive only inside. So that's how the positive is getting outside the cell, and the polarity is getting established by the action of ATPases, and that's our all action potential, right? So here what is happening, that I've drawn a structure of our cell membrane of our neuron. Here we have the leaky potassium channels in the black. Here in the green we have the sodium voltage gated channel, which we can say that this is the inactivation gate here, which is only present in the VGC of for the Na positive. For the K positive we have the potassium voltage gated channel, and in this oval sphere where you have the sodium potassium pump. So generally this is just one segment of our whole membrane of our neuron, right? So coming back to the sodium voltage gated channel, what happens that in the resting condition, when we have the voltage of approximately minus 70 millivolt, this has just happened that what this one gate is opened, and